Hello, everybody. Thank you for coming to Cafe's Research Panel 2022. The event's going to be running from 7 and we might end a little before 8:30. So this is the Cafe Research Panel. Hope you enjoy. Our general schedule for the event is first going to be just general introductions of our speakers. Then we'll go on to each presentation of the speaker's research. And during the presentations, there will be a cafe logo in the speaker's slides. And the point of it is supposed to be an Easter egg hunt. And if you want to participate, you just have to count how many cafe logos you see in the speaker slides. And in the raffle at the end of the event, there's an option to comment how many Easter eggs do you see. And the people that get it right will be entered in a raffle for a $25 gift card. And there's also going to be a Kahoot gift card as well. So whoever wins that Kahoot. So pay attention to the presentations very well. And at the end, we'll have a feedback. So that is going to be the general schedule of the event. And our guest speakers are Professor Levante Diosati. Would you care to introduce yourself?
I'm the professor of food engineering. I've been here since 1980, and I love to be here. I'm really impressed by the fact that students have started a club on food engineering, and where there's food engineering at U of T, I like to help. So here I am.
Thank you, Professor Diosati. And then we also have one of Professor Diosati's PhD students, Folake Oyewole. Would you care to introduce yourselves?
That was good pronunciation, nearly perfect. My name is Folake Oyewole, and yes, I'm a PhD candidate, ably supervised by Professor Levante Diosati. And in the course of my presentation, I'll tell you a little bit more about myself and a little bit more about my research. Looking forward to the experience.
And then our final speaker will be Nayab Nagri. Would you like to introduce yourself?
Yeah, hi everyone. I'm a master's student in Professor Diosati's lab. Again, I'll go more into my background in my presentation, but I'm really happy to be here and I look forward to talking with everyone.
So thank you for our speakers for coming, and I hope that you all enjoy their presentations. So once again, I want to remind everybody to keep an eye out for the Easter eggs, because there will be a chance to win a gift card at the end of the event if you guess correctly how many Easter eggs there were. So Professor Diosati, would you care to share your screen?
Let's try. Okay. All right. So thank you for inviting me. It's a pleasure to talk to you. I'm always impressed by the fact that we have students that are interested in food engineering, and I hope that interest is going to keep going. Food industry is the world's biggest industry, so we're in the right place. You were asked me to talk a little bit about my research, a little bit about food engineering, a little bit about how I got there, so I will do that. So food engineering is sort of at the intersection of at least 4 different disciplines: chemical engineering, biochemistry, agriculture, biochemical engineering, food science. Also, I'm not showing on this slide, in the other dimension, that we have also a lot of people in civil engineering and mechanical engineering who are working in the food industry and therefore qualify as food engineers. In Canada, there is no program for food engineering as such, undergraduate, the only exception being the one in Laval. So what is food engineering? It is really, in the definition that I use, is the dealing with the application of chemical engineering principles to large-scale processing of food. I'm not welcome in the kitchen, but ask me anything, we'll make it in 5-ton lots or bigger. So how does one become a food engineer? There are many ways of doing it. I'm sorry that Don Mercer didn't make it, because his career path is equally convoluted and difficult, but I started out, I got my chemical engineering degrees at U of T, and my doctorate program was in catalysis, which sort of set me up for going into petrochemicals. I was hired by a general engineering company in Mississauga, and started working on a variety of projects and also started developing processes for this company. I became the director of research and development when the company was bought by a food company that owned an edible oil processing plant in Saskatchewan, in Nipawin. And quickly I had to become an expert in edible oils and food, and I am still an expert in edible oils. So based on that experience, I was invited actually to become a professor of food engineering, starting up the program here, and was working on all kinds of Canadian problems, and I still have some interest in there. But about 1991 and 92, a gentleman called Venkatesh Manar, who was working for the United Nations on salt fortification with iodine, contacted me and said, we need a problem with iodine and iron. And so I started working with salt and micronutrients, and that has been going on for the last 25 years. And I'm involved in food fortification programs and with several different things and several different projects in many different countries with a very large number of people. So what are micronutrients? They are key chemicals required for health in very small quantities. And there are all kinds of uses in the body. We actually have about 50 different micronutrients on different scales, but the lack of iodine, iron, and vitamin A adversely affect 2 billion people. If you have for example, an iron deficiency, the iron deficiency decreases your ability to work. And so if you can't work in a country where physical labor is a major source of food, your food is not as good. So therefore you become even more micronutrient deficient and even less able to work, and you earn even less money. And this vicious cycle goes on and drives people into deep, deep poverty, and it drives their kids into deep poverty. And they end up with kids that are stunted, have reduced mental capacity, and increased mortality. So what can be done? Well, the ideal thing is to diversify your diet so that you get all the micronutrients that you need. Problem with this is that it takes a long time. It changes some societal things that you're used to. Even in North America, where we have everything that we possibly could want in the way of food, we haven't been able to convince the population to eat a healthy, diversified diet. We end up with diseases like diabetes and heart disease and cancer. You can get around a deficiency by supplementation. You can take a pill, you have a certain amount of vitamin A, a certain vitamin B, and this helps on the short run. But the problem with this, it really needs a medical overview, because if you have an uneducated population, you might end up people thinking that if one tablet is good, then 10 tablets would be better, and poisoning themselves. Or ultimately just getting them to take a tablet might be difficult. Taking them regularly on a well-defined time or day is also difficult. So supplementation becomes very expensive because of this requirement of having a medical overview. Food fortification, on the other hand, is rapid. It almost immediately provides the micronutrients. It is relatively easy to implement, although there's always political challenges to its implementation, and there's some technical challenges. But it typically is very cheap. To give you an idea, I'll talk about iron fortification later. Really, to bring the iron level up to the required level, it'll take only about 25 cents per person per year. So you have to pick a carrier for micronutrients. You can't just put micronutrients on anything. You put it on porterhouse steak, the number of people that would actually benefit from it would be very limited. And the amount that they would eat would be variable. So it's not really a good carrier. A good carrier is consumed by everybody in the target population. Salt is a perfect example. We all eat salt. It has to be centrally or commercially manufactured so that there is a point in the process between the manufacturer and the intake where we can get in and actually do the fortification of the product. You want something that has a uniform daily intake, and you want that intake to be independent of social status. You want them to be inexpensive, and you want to make sure that you can't overdose. So I dealt with two particular desirable carriers. There are many others. There are not that many, but there are many others. Salt is a very good one because everybody consumes salt. And all of the salt comes through some sort of a commercial source. So there's always a position in this chain of delivery where you can actually add micronutrients to salt. And the big thing is that about 500 million people around the world are agriculturalists and are poor. They grow their own food. They don't buy any food. So they can't be reached by any processed food. So flour, fortified rice, fortified noodles, none of that actually reaches this very large segment of the population. Surprisingly, the daily consumption of salt is very uniform. Within a certain society, it is within plus or minus about 10 to 20%, which is as good as your prescription drug is. So we have a very good handle of how much micronutrient you can deliver safely without overdosing. I also mentioned another typical one, which we work with quite a bit, is tea, because in South Asia and in China, but South Asia specifically, everybody, even the poorest of the poor people, buy tea and consume tea. Now, salt is widely iodized, and 86% of the households in the world get iodized salt. And this is a big triumph for food engineering. It started 100 years ago this year. And as you see, we have essentially eliminated iodine deficiency disorders, which were serious problems with essentially nervous development, cretinism, reduction of IQ. A low iodine diet can reduce your IQ from 120 to 125, where you are, down to about 70, which is like a 4-year-old kid. The problem is that iodine is quite reactive. So if you take iodate, which is the typical form of iodine that's added to salt, and you add iron in a ferrous form to it, the iodate is reduced to elemental iodine, and iodine here actually sublimates and is lost. Not only that, the ferrous iron, which is highly bioavailable, is oxidized to ferric, which is less bioavailable, but it also is rust-colored and tastes terrible. So we have a real problem in trying to prevent this interaction. So we decided to get around this by microencapsulating one or both or either of the two micronutrients in the salt. Oops. We ended up, after many years and many different processes, with a process where we're making a premix, which is added to salt with a ratio of 1 to 100. Now the premix particles from here to there is about 0.5 millimeter. It's about the size of a grain of salt. The central core is ferrous fumarate, which is highly bioavailable, but is dark red in color. On the outside, we have titanium dioxide, which is bright white. It is the key component of white paint. And then on the outside, we put a moisture-proof coating of a solid fat. So this is what it looks like. We start with ferrous fumarate powder. We put it through an extruder, which makes angel hair pasta. And all of you, I'm sure, know what I mean. They're thin, long slices. We chop them so that their aspect ratio is 1. We cover them with the white paint, and then we encapsulate it and put it into salt. And you can see the salt crystals are there, and the little bit of the cylinders are included in the middle of it. Project involved all kinds of things, visiting meetings and looking at how salt is used, how salt is bought, how do you measure the iodine in the field, how do you measure it in the plant. All of these things have to be looked after. But at the end, it turns out to be very, very positive. We had a test with 3.5 million school kids in South India, and they are all poor, and they all get 1 hot meal a day at school. And being India, it's vegetarian. So the school lunches were prepared with our double fortified salt for 8 months. And within 8 months, the number of anemic children dropped by 34%, which indicated that we managed to cure 1 million children of anemia. Now, in 2008, we had another much larger scale test in Uttar Pradesh state in India. There, we reached up to 60 million people. And over a year, increased the women's iron status by 20%. We worked with a company in Jaipur, India, and we transferred our technology to them, and they actually built a plant. So we have a plant there now, which is very modern, very nice looking, and we can actually make enough iron premix to feed 100 million people. Right now, we have an efficacy trial on fortified salt, which not only contains iron and iodine, but also contains folic acid and B12, all of which are important for women's health and prevent childbirth problems during childbirth, either maternal death or infant death, or alternately different birth defects. And Bill and Melinda Gates Foundation is funding an efficacy testing of multiple fortified salt, which also includes zinc. So there are 5 things now on salt. And this is being run in Haryana state in India, and the project was started just now. We have another project in Cambodia where we add thiamine because they're very short in thiamine in their diet. And so one of our colleagues from Mount St. Vincent University is running a project in Cambodia to eliminate the problem of infant beriberi, which is folic thiamine deficiency. Just to give you an idea, there's all kinds of things you can do. This is my list of projects at one time. So there is tea, and there's all, oops, come back. Sorry about that. I'm a little fast with the mouse there. But anyway, so there is problems with tea, and we deal with a number of different people, Unilever specifically, funded by different organizations, including an alumnus. We also have students by the Schlumberger Foundation. You will hear one of them. We'll be talking about native soft drink from Nigeria. We talked about moringa, which is a plant in the tropics. Hairy amaranth, which I do with one of my students from Mexico, who's a professor there. Other granado beans, which we do, and a professor, a student of mine, was in Chile. And then there are Canadian projects where we do canola for biodiesel and food, and also for putting out minor components from salt. And occasionally I do a bit of consulting, for example, in Indian bread. So there it is. The salt flats are beautiful. They are a big industry. They are very influential, and they contribute to the health of the people. One of my favorite slides, this slide in green shows where I had graduate students from. It's still missing Afghanistan. I have one there. And the red ones, where I have students of mine who are professors at this point. And with that, I'm finished, and I'm open to questions.
Thank you, Professor Diosati. So we'll open a 5-minute Q&A. Does anybody have any questions? Yes, Melinda.
Hello, professors. Thank you for introducing us to your research. And after listening to your introduction, your research is truly impactful and very interesting. And I guess one question I have is, what are the current challenges that your research is facing? Yes.
Okay. You can interpret that question different ways. One of the challenges that every professor always faces is funding, make sure they have enough money to run your research. But we have a number of different problems that we've been faced with. Typically, the most current one is that titanium dioxide, for example, is a very, very bright white colored material that is widely used in foods as a food colorant. Now, the European Union found that some of the titanium dioxide used is nanoparticles, And nanoparticles can actually go directly into the bloodstream because they're so small that the gut wall doesn't prevent their transmission. And so just recently, the EU has banned titanium dioxide in foods in EU. So we right now have to scramble for something else that will make our particles white. That's a typical current challenge, but we always have interesting challenge. Like I deal with people in Ethiopia where there's a huge problem with birth defects. And they are asking us to see if there is a way of providing folic acid through salt relatively quickly and inexpensively. And so we have two different approaches to it. And hopefully we'll be able to actually get one of them widely distributed in a fairly short period of time. I can always find 20 other projects, by the way. There's so many different things in food that you can do. It's a question of time, money, and age. And the age is becoming more of a problem as we go along.
Thank you, Professor. Those challenges sound so interesting.
Any other brave soul?
Bipasha, would you like to unmute yourself and ask?
Yeah, sure, thanks. So that was a really cool presentation, Professor. I'm from India, so I particularly kind of related to what was being said, and I found it extremely interesting. I might have missed this in the presentation itself, but I'm very new to this field, so I may be completely wrong, but my understanding is for food fortification, typically, typically it's directly consumed by the user. But with tea, it's steeped into the water. So how did you get the iron into the water?
Very good question. Actually, tea is a very difficult problem. It's very easy to add iron to anything, but what happens with tea is, first of all, the polyphenols that are in tea, the alkaloids, they're there. They complex with iron and they grab the iron and make it unavailable. So you can add any amount of iron and it just goes through the person without any benefit. So we have two different approaches. One of them works in India and one of them doesn't. So in India, a lot of the people, if not all of them, if not the majority, drink tea with milk. And you'll correct me if I'm wrong, but typically the poor people tend to boil up milk with tea leaves or tea powder, actually, and drink that with lots of sugar. It's quite nice, actually. But problem if you add iron to that, all of the iron is absorbed. So we need to microencapsulate the iron in such a form that it's not released until it's in the gut, in the stomach acid. So we're encapsulating iron in a polymeric matrix and then letting it go through that way. The other thing is we are using typical chemistry by trying to use another chelating agent, which will actually displace the T tannins and provide iron in a chelated form that is absorbed. And that is done by a compound called EDTA, ethylene diamine tetraamino acid. EDTA grabs onto the iron and EDTA will take it right into the bloodstream from the gut. So for black tea, we have a relatively easier time. We found out there's a stoichiometric ratio between EDTA and iron that actually allows the iron to be absorbed. We stick an iron compound onto the tea leaves by spraying it on with a glue, the glue being a starch usually, or HPMC, another edible polymer. As soon as it hits the water, it dissociates, it is diffused out, and then it's consumed. So we still have a lot of work to do there, but I think our black tea approach, which is targeting East Africa, actually works, and is if I'm lucky, by next year, it's going to be commercial.
That sounds great. Very innovative ideas. I just had a quick follow-up. So was there a particular time that this tea had to be steeped for? Were there instructions that users had to follow in order to get the entire benefits?
Well, usually what you try to do is not to change anything that the normal consumer would do. If you make any change, think about even yourselves who are, highly educated and sophisticated, you really don't want to change your routine. So what you want to do is, if you're making any kind of an inroad with fortification, for example, what you want to do is you want it to be totally transparent to the consumer. So you steep it for the same time, you do it the same way, you add the same amount of sugar, you do everything exactly the same thing. Only difference is that you also are drinking a milligram of iron, which is enough to elevate your iron status up from the danger level to being reasonable. And India is very, very important because 54% of Indian women are anemic, independent of social status, which is the really interesting thing. It's not just the poor people, it's even the, well-educated, well-to-do people. And so there is a demand now for products in India and by the more affluent people as well, to actually get some higher levels of iron specifically and some of the B vitamins.
Yeah, I completely agree, because in fact, it's the more well-educated and the affluent people who pay attention to these deficiencies, and the not so well-off people don't even realize. So the demand is unfortunately higher unequally. Yeah, and to your point about the not changing the user experience, I'm taking a course on user experience, and that's exactly what was discussed. So it was nice to hear it like being actually applied in industry. Yeah, thank you so much.
It's nice to get feedback that you're doing actually stuff that's reasonable. That's good. All right.
All right. Thank you for the Q&A session. I think it's time we move on to our next speaker. So Falake, are you ready?
Yes, I'm ready.
Awesome.
So I'm just going to try to share. Okay. All right. So Prof has done the hard work. I'm pretty excited about that. So I'm just going to feed off what he's done. So hi again, my name is Falake. Super excited to be here. I'm a PhD candidate in the Department of Chemical Engineering and Applied Chemistry, and I'm ably supervised by Professor Levinti Diashadi, who is here from the Food Engineering Group. My thesis is focused on iron fortification of hibiscus sabdorifer beverage. In the course of this, I will expatiate and talk more on that, but I thought I should start with, a synopsis of how I found myself in food engineering. So at a very young age, I had the opportunity to travel to the States, and I was so surprised by how things worked in the States. And they had running water, constant running water, or electricity supply in my country. And I was just surprised, and I wanted that for my country. I wanted, to see all these fantastic things that were happening in the United States happening in my country also. So that's where, I got to start thinking about engineering, and that's where my love for engineering developed. Then I was opportune to interact with a protege of my mom's, who convinced me that chemical engineering was like the most versatile engineering in the world. So, I was like, okay, I'm going to be a chemical engineer and I'm going to solve all the problems of Nigeria. Got into undergrad in a well-known one of the well-known universities in Nigeria, Obafemi Awolowo University, Chemical Engineering. And during the course of my program, I had the opportunity to be placed in 2 food and beverage companies for like an industrial training, like sort of like the PEY co-op that you guys do here, right? And I got the opportunity to work in a dairy company and also a brewery company. What I found though was I felt the job of the chemical engineers were very monotonous. I didn't see them doing anything really innovative or exciting. And remember, this was what I wanted to do. I wanted to make a difference, right? So I basically thought, okay, I need to go further, you know, like do something else to discover what I was going to do. So went up to the United Kingdom, University College London, got my master's degree in chemical process engineering. My research had nothing to do with food. However, during my stay there, I fell in love with research, and I identified research as a way that I could actually affect the change that I so wanted in my country. So getting back home, I started working as a research scientist in the foremost research institute in Nigeria, the Federal Institute of Industrial Research. And I was working on, value-added processing of agricultural resources that were locally available. Also, we're looking to substitute out conventional raw materials in the food and agro-allied companies with what was available locally, right? So we're trying to build the economy of our country. Exciting, but frustrating because we did not have the funds to back our research. And at this point, I was actually going to bow out, join the industry like all my mates were and make some money. But then through a string of fortunate events, including Professor Diashade accepting to supervise my thesis and bagging a scholarship, the Schlumberger Foundation Scholarship, I found myself at U of T. And now with my experience, I believe I'm well embedded in the food engineering world. So my research, as a background, I'm focusing on iron deficiency. Prof has spoken so much about micronutrient deficiencies and what those are, but iron deficiency is actually the most prevalent deficiency, micronutrient deficiency world. In fact, it's the most prevalent nutritional deficiency. And it's 50% of the world's anemia cases are actually attributed to iron deficiency. It affects Africa and Asia the most, like it's quite prevalent in these countries, and they actually contribute 85% of the absolute anemia burden in high-risk groups. And these groups are like, preschool age children, premenopausal women, and my research is actually targeted at sub-Saharan Africa. This is the population that I'm targeting. Prof has spoken about salt and tea. And yes, tea is taken in Nigeria, but it's, we don't take tea that much. And so I looked at the resources we had and I considered what we could, add value to, and also add this micronutrients to that will resonate with the population we're targeting, and they will be eager to consume this beverage. So that led me to my food vehicle of choice. Prof touched on the importance of the food vehicle, that when you're fortifying this, the food vehicle you choose is absolutely important, because you don't want to just have a product that nobody's consuming. You want to make sure that there is high consumer acceptability. And so I actually reviewed a couple of herbs. I brought them from Nigeria. Prof was kind enough, and I reviewed them, and we decided to go with the hibiscus beverage. One, because it's already commonly consumed. It has a very refreshing taste, and also it is perceived to be nutritionally and even has some therapeutic benefits. It's presumed to have nutritional and therapeutic benefits. And so I started working on this, and some of the common names, just so maybe it will be familiar to somebody, it's hibiscus, roselle, and sorrel. In Nigeria, we actually refer to it as zobo, and in Sudan as kakade. These are sub-Saharan African countries. So also, one thing Prof touched on was how capital intensive the project is. We don't want it to be that. And this is a beverage that is already produced on a mass scale in Nigeria. So it seemed like an ideal food vehicle that could cover the gaps in other food fortification initiatives targeted at iron deficiency. Okay, now the gap. So we know that it's rich in iron, but it also contains these polyphenols, just like tea. And these polyphenols we know will inhibit the iron absorption into our body. Just as you see here, it forms this complex, a chelation complex, that is difficult for our bodies to digest. And so my research is basically trying to prevent this interaction so that the iron, both the one that is inherently present in the herb, as well as the one that is added as a fortificant, are available for absorption in the body. This is my research at a glance. I thought I should just put it on a slide so that, it'll be easy for everybody to understand what I'm doing. Target population, I did highlight Nigeria, and you can see here a woman, a mother, and a child. And you can see the signs of deficiency on them. And these are the people we're trying to improve their lives. I'm working with this, the calyces. And then this is turned into beer. It's just an aqueous extract, really easy to produce. It's not cost intensive at all. And then we look at the beverage before fortification and after fortification. This is the bad person we're trying to prevent, because we want that, because we could add a ton, just as Prof said, of the iron into the beverage and say we fortified it, but then the body is not able to absorb it. What's the essence of that? And we do want results. So we had to get rid of this. And that's when we introduced the disodium EDTA into the beverage, and through results, we've been able to free up the iron in the Fe2+ form, the more bioaccessible form. And that's been fantastic. So key findings: the beverage pre-fortification doesn't contain enough iron. It's worthy of note because already they're consuming it, believing that it's going to improve their iron content, right? But no, it doesn't do that. And we also identified, this is the target, this is concentration that is targeted, by the way, 30% of 18 milligrams per day, which is what is recommended for pregnant women, right? And we have the targeted volume to be 250 ml, because this is what is, with research, we found that soft drinks, this is the volume that is not consumed by most people on an average daily. Then the iron polyphenol complexation is reduced when the competing chelator is added, the disodium EDTA. The effect was more noticed, however, with the added iron as opposed to the iron that is native, which begs the question of cost effectiveness, because we're thinking if we're able to release the iron that is inherently present, we don't have to add more iron. And when I say cost, I shouldn't say cost effectively, total cost, right? The total cost of fortifying the beverage and making it bioavailable for the consumers. So research opportunities, of course, multiple fortification. I'm sure Prof mentioned during his presentation that multiple fortification is less expensive, because if we're able to add on, as many micronutrients into one food vehicle, then it's cheaper than if we're taking each micronutrient and adding them individually. But that also brings complications of interactions between the fortificants, as well as interaction between the fortificants and the food vehicle. So another thing you could look into is the design of an encapsulation system. We're just looking into liposomal encapsulation system for the beverage currently. Also adapting the technology to other polyphenol-rich plant foods. We know that the world is talking so much about plant-based diets, but we also know that there are these inhibitors. So research like mine can be adapted to other foods that are rich in polyphenols, other plant-based diets that are rich in polyphenols. And of course, research is inexhaustible. There's always a new idea to dig into, like I wrote here. Thank you very much for your time, and I'll be happy to take some questions.
Okay, thank you, Folake. Does anybody have any questions? Melinda?
Yeah. Thank you so much for your presentation. It's truly inspiring listening to how you develop your passion in chemical engineering. So a question that I have is, in your research, did you experience the problem of iron impacting the taste of the beverage, like what Prof just mentioned in the salt fortification?
Absolutely. And this is definitely part of my research. But the thing about our research is there are layers to it, right? So the fundamental problem we have identified is that this ion would interact with polyphenols. We do not want to get rid of the polyphenols. So we want to find a way that they can both coexist with by adding a competing chelating agent, right? So yes, we will definitely have to look into that. And that's where the need for the liposomal encapsulation system that I was talking about comes in, where you encapsulate the ion and prevent it from, interacting with the beverage, affecting the taste, basically. That's all, because the ion would not necessarily interact with the beverage on its own, but it would affect the taste if it's just added through direct mixing. So that's the next layer of the research. Thank you for asking the question.
Thank you. And I would really like to try the beverage one day.
Oh, it's really refreshing and it's quite available. I don't know, even here in Canada, it's available in some Indian stores, I believe.
Oh, okay. I'll definitely search that out. Thank you.
All right then.
Any other questions? Bipasha?
Hi again. Really excellent presentation once again. I have two questions, one related to your research and one kind of related to your journey. The first question related to your research is, and this might be more of like a funding or like how are research problems even designed sort of question. But I know like a common theme between your and professors' presentations was iron fortification. And I'm sure there's a lot of other micronutrients that require fortification. So how is it decided that iron is the focus? And also like, where is the research for the other kind of micronutrients as well, if that makes sense?
So there is a lot of research for each and every micronutrient you can think of. However, there are limitations for each of them, and the iron is highlighted because the problem of the polyphenol interaction is something that hasn't necessarily been addressed fully. And that's where research goes, right? Where there's still a gap. You want to keep digging into that area to make sure that you solve it before you can move ahead into the next problem. So there are tons of ways that this, in fact, within our research group, if you listen thoroughly to Prof's presentation, you'd have heard of quadruple fortification of the iron. Yes, and because we do know that many of these micronutrient deficiencies don't exist on their own. There's always you're iron deficient, there's deficiency in folic acid, there's always, it's always interrelated. So definitely you want to address as many micronutrient deficiencies as you can, but then you have to do it in a very scientific way because there are interactions to consider, there are other things that have to be considered. Also the target population. So when you look at a target population, they might be more deficient in a particular micronutrient more than some others. For instance, I will tell you that something like vitamin D is not necessarily a problem in a place like, you're nodding your head, in a place like Nigeria or maybe even India, but in other parts where getting as much sun, especially for dark-skinned people like us, is not easy. It's not as easy. So those are things that definitely are taken into consideration when designing or developing the project. We like to say it's demand-driven research, right?
That makes sense. And I'm glad you mentioned vitamin D because of COVID. I think almost everyone is suffering from vitamin D deficiency.
Wow.
I know I am.
And because of COVID, but it just highlighted it. COVID highlighted how, the importance of vitamin D, yes.
And the other question I had related to your journey was you kind of mentioned that your experiences in chemical or food engineering industries were not as exciting as your research experiences. So where do you see yourself going after your PhD? And this might be a question you haven't explored as of yet, so it's completely fine to say I have no idea, but just wondering what's next.
It is a question I've explored, definitely. I mean, I've had some years to think about it. For me, research is at the heart of anything I want to do. So one thing I wasn't necessarily exposed to was research R&D sections, or like the R&D department in these industries. Like I was on the on the ground with the plants, like we were monitoring the unit operations as chemical engineers. We weren't necessarily looking at what the R&D department was doing. And I will say, particularly for places like Nigeria, I can speak to Nigeria. I used to hear of this, they will tell us that they were bringing in the secret ingredients. So for Nigerian brewery, for Guinness, for instance. So I thought even the people that were mixing did not necessarily know what was going into the mix. And for me, that was just crazy, because I'm like, well, this thing that you're importing that is the secret ingredient could be next door, right? And it could be something that you can easily get here, but there's just this myth that something is coming in, and everybody was ready to accept it that way. And that wasn't just what I wanted to do. I wanted to be in the mix and know what I'm doing and be innovative and make a difference. So what's next? Still probably research, maybe in the industry. Who knows? Maybe consulting with a developmental agency somewhere. That'll be nice.
Sounds cool. And I'm not sure how much time it's been, so I just want to ask a real quick question just to follow up. So did you find that kind of involving yourself in R&D positions in industry necessitated higher education or beyond undergrad?
No.
Okay.
That's the honest to God truth. However, knowledge is something I'm also passionate about, like knowledge, and I intertwine knowledge with experience. So if you follow the trend of my journey, I've been to places, and I find that in different places, different things apply. And I think this has expanded my understanding of that phrase, demand-driven research. Because I know that when I'm in Canada, what I should be looking at is different from what I should be looking at when I'm in Nigeria. And the beauty also of my opportunities, I've been able to expand my network. I've met Prof. I mean, so things like that, definitely taking such opportunities expands your network and knowledge. So you can never have too much of knowledge, but definitely you can walk in the R&D sector. You don't have to have a higher degree, at least to my understanding.
Okay, great. Thank you so much for your answers.
You're welcome.
Thank you, Falake. That was really insightful. I don't know. I thought it was in some ways also like really nice to hear from you that, oh, you don't need a really high degree in order to make it there. So
hold on, maybe Prof has something to say about that, but I'm thinking that Prof, do you want to chime in?
Well, there is occasionally feeling that if you go all the way to a PhD, then you lock yourself out of a number of jobs. It's not true. Depending on the companies, depending how open, progressive they are. For example, when I went out into industry, my boss was also a PhD chemical engineer. We consulted, and we didn't necessarily put it out that we're PhDs because then they think you're too expensive. But certainly it's appreciated. The extra knowledge is useful, and so. She's right. You can never have too much knowledge and too much experience. So I've been very fortunate in doing a great number of different things in different fields. And I'm not very deep in anything, but I'm certainly broad in many, many different areas. And that helps a lot in the food because it's such a large field. And Falake didn't mention the fact that her Schlumberger is very prestigious. She's got a scholarship for Schlumberger is a company that does instruments for oil fields and everything else. Actually, it's called the faculty of the future. They take people that they think will become appropriate members of faculty in their developing countries or developed countries, and they finish. So the Schlumberger is a very prestigious thing to have.
That's really impressive. All right, thank you so much. Our final presenter, Nayab, are you there? Yep.
Hi, everyone. So let me share my screen real quick. Awesome. All right, so hello again. My name is Nayab Nagri. I'm a master's student in chemical engineering, and I'm in the food engineering lab under Prof. So quick background and how I ended up in food engineering. I'm from Mumbai, India. I then went on to do my undergrad at the University of Illinois at Urbana-Champaign. In my time there, I worked in all kinds of industries. So I worked in acrylic and fiberglass, and then later on resins and adhesives. After I graduated, I went on to work in pharmaceuticals for a company called Puma Biotechnologies based out of LA. In my roles in the company, I worked in chemical manufacturing and controls. So that's a regulatory department. And I worked in quality affairs and data platforming. I then, after that, went on to work for, came to University of Toronto, where I was looking for a research opportunity and something to sort of strike my curiosity, as it were. And I came across a new field. I'd never done anything related to food engineering before then. I'd never even heard of the field, in complete honesty. Micronutrient fortification kind of caught my interest, and emailed back and forth with Prof, and he was happy to have me in lab, and here I am. So I'm only in my second semester here at University of Toronto, and yeah, we'll go in a little bit detail into my research now. So yeah, I'm focusing on fortification of milk tea, specifically the scaling up of the spray drying process. And yeah, you've seen the slide. You've heard these points before on two separate presentations, but I'll go through them very quickly. Why do we fortify food? We fortify food because it's a cost-effective, sustainable way to treat micronutrient malnutrition. Why did we choose tea as a vehicle for fortification? Well, for the Indian subcontinent, it is ideal because people drink 2 to 3 cups of tea a day, and it's consumed ubiquitously by the population. Iron fortification is super important because the diet inherently is limited in iron intake, and the population is susceptible to iron-related diseases. So a quick overview of what the spray drying process looks like. So on the left is a schematic of the spray drying process. So you have a feed tank that has your iron salt in a aqueous dispersion and your encapsulant material that is fed via atomizer and is combined with a hot drying agent, usually hot air. In our case, though, we use an inert drying agent that's just to prevent oxidation. And you have essentially a dried product coming out, and you exhaust your hot air. So the process is a little better explained from the perspective of the iron particle to the right. You have your suspension of an iron salt, you spray dry it, get rid of the water, and what you're left with is an encapsulated iron salt. So what is the challenge in terms of scaling up? We want to go from a lab or a bench scale to pilot and then to commercial scale. Sorry. There we go. In terms of what the challenge is for me is to find a model that works independent of scale. You can approach the problem from a couple of different angles. You can do it from a thermodynamic perspective or a sizing perspective. For us, it's crucial to do both because we want the encapsulated particle to be small enough that it is at the same scale as the tea leaf. But thermodynamic is better for scale up because you can adjust the thermodynamics of your spray dryer more easily. Most models can describe parts of the particle formation, but not all of them. CAD and CFD do not work. I found this out the hard way. If you try modeling the process in CAD and CFD, you will go through lots of complex problems. And what the main limitation is that too much happens too quickly and CAD and CFD cannot keep up. So just to elaborate on that problem, I have a picture of a nozzle. So these are the atomizers that feed your solution and your drying agent into the spray drying chamber. You can see that there is, your particle forms almost right outside the nozzle. So it's a very quick process, but it's also you're encapsulating and drying simultaneously. And that problem is only exacerbated when you go from 2 fluid to 3 fluid nozzles that have 2 layers. So this is the challenge. And I went ahead, like I said, and I worked on the thermodynamics a little more. And what you end up with is a sort of equation that deals with all of these factors. So you have your spray rate as a function of temperature drop across the spray dryer, your exhaust temperature, the humidity or absolute humidity of the air, the thermal conductance of the spray dryer, and then the thermal properties of your feed solution. Of these, the most important one is the temperature drop across the spray dryer for a variety of reasons. But what's crucial about this sort of equation style model is that it works independent of scale. All of these parameters can be adjusted on the spray dryer or by altering your feed ever so slightly. The downside to this model is that it is extremely specific to the compound, which comes from this last property here. So if you change your salt for any reason, or you decide to go from one iron salt to another, you have to essentially redo the model. Another problem with this, like I said, you describe parts of the process, but not all of them. So another problem with this is that it discounts all sizing parameters of the particle. And like we said, for T research, or for any scale up, we want to maintain the size of the particle at the same level as the T leaf. So how did we end up, how did I get to this model? It actually starts with first law of thermodynamics, which sounds ridiculous because that's second year undergrad. But you start with first law of thermodynamics, you apply that to the open system, Newton's law of cooling, and what you end up with is a heat capacity analysis. So a very elaborate calorimetry experiment that you have to work your way through to get to this model. Peripheral to my research is sort of understanding things happening at different sizes. So really, I think it's important to understand not just lab scale, but also eventually you're going to have to take this to commercial scale. So understanding what's happening in the commercial industry is also important. In terms of size, we go from lab scale, which is liter scale, essentially, and then you're scaling up by about 3 orders of magnitude when you talk about scaling up a process. So you go from lab to pilot to commercial, each one going up by 3 orders of magnitude. At commercial scale, you need to then find commercial solutions that exist. And 2 of the main competitors that make or manufacture pilot and commercial scale spray dryers are GLAT and GEA. They're the 2 sort of larger ones in industry. Another aspect of my research is to evaluate alternate methods to spray drying. So producing a powder from a liquid is not just exclusively related to spray drying. You have other options, and this is by no means an exhaustive list of them, but drum drying, layering, and flash drying are also options. They all produce slightly different results in terms of the finally encapsulated particle, but if you can modify them to work, that's another option. Also, I just like the name Drymeister by Hasegawa. So that was just a cool name to include. But yeah, that is my research. If you have any questions, I'll be happy to take them now.
Go ahead, Melinda. Please feel free to unmute if you ever have any questions as well.
Thank you for your for introducing us to your research. And I'm actually currently in my second year Chem Eng, so the thermodynamic knowledge you mentioned is really exciting to know how the knowledge I am learning can be applied to really great things. Yeah, and a question that I have is more related to your experience. You mentioned that you transferred from pharmaceutical industry to food industry. I'm curious as to what the transition was like, and did you experience any difficulties for starting the food industry?
That's actually a very good question. And the answer is no, because the two industries have a large deal in common. And since my topic is largely commercial sizing or moving between lab to commercial, it actually helped to have worked in a large plant and sort of understand that experience of it, and then sort of see, okay, so this is what we're doing in lab, and I know what we need at industry scale. So moving to that is helpful. Also, spray drying is not limited to food engineering. Pharmaceuticals also use spray dryers. So if you end up reading a lot about these papers, a lot of these papers are pharmaceutical spray drying. So it's sort of, it's an interesting sort of diagonal transition for me. So no, the transition wasn't super difficult. And I think the mobility between the two fields is pretty high. So
I see. Thank you.
Yeah.
If I can add, having industrial experience is very useful and quite transferable from one part of chemical engineering to another. So Naive coming in brings a completely different perspective from our average student that has never really been in a big plant. When I used to teach food engineering, I used to make sure we take people out to plants to see how big they are and how things are done on a larger scale. And it's a very useful and important knowledge.
Sandy?
Yeah, first I wanted to say that all of the 3 talks so far have been really interesting. It's been so interesting to, like, I've heard about like things being like fortified with like micronutrients and stuff, but it's interesting to know that like there's research about that being done like here at U of T. And my question for you was, so you mentioned that you're working on like scaling up using the spray drying method, but you also mentioned a few of the other drying methods that were used. So I was wondering why specifically is like spray drying the one that you're focusing on, or yeah.
So in lab, currently what we use is a spray dryer. It's also one of the most explored methods on the lab scale. A lot of these other methods are sort of larger pilot and commercial scale. So working with them is a little difficult and not really cost effective. Spray drying is a very cost effective method that is well researched and very fairly common. So that's why spray drying. But in terms of exploring other options, I think it's crucial to not limit ourselves to just one method. So yeah, I hope that answers your question.
Yeah, it did. Thank you.
Bipasha?
Hi again. Really cool presentation. Like that it was a different kind of the more thermodynamic angle rather than like a biological angle that's being looked at. So that was cool. I had like a clarification question for you, which I'll ask later. But the first question was, I noticed in your first slide, you said you're undertaking an MEng,
Yep.
So not an MASC.
No.
What was the thinking behind that decision?
So I was through my undergrad, I never did research. I was purely focused on working in industry. U of T was interesting because it gives you the opportunity to do a course-based master's, but dip your toes into research. Sort of not in a MASC sense where research is the primary thing you're doing, but the MEng gave me the ability to sort of dip my toes into something I had never done before. And I think I've come out in my time, I've become definitely a better engineer, having worked now in industry, but now also in lab. So you understand both sides of producing something. So
That makes a lot of sense. Yeah.
it was also one of the main reasons I ended up choosing U of T, was the ability to do a MEng project.
Right. Yeah. Because I think in the States, it's optional to undertake.
You do one or the other. You either do an MASC or a research-based master's or a course-based master's. You can't sort of combine them.
Do research-based masters still exist in the States?
They do.
They do? Okay. Last I checked, I wasn't able to find any, but good to know that they exist. Right. Oh, yes. And my follow-up question to that was, so where do you see I asked the other speaker as well, where do you see yourself kind of going after your master's?
I think I'll end up back in industry, but
Okay.
I don't want to say one way or another. Who
That's
knows?
fair. Yeah.
But the working back in industry has always been my focus. So that's definitely where I see myself heading.
Okay, makes sense. I think, yeah, that's all my questions for now. Thank you.
Sasha?
I'm not sure. It might be a silly question, but I'm not really sure. But I just want to try to understand more about the process of scaling up from a lab to commercial size. So you started off with like the scientific model in the lab size, and then you scale it up. And I think since like the scale is a lot larger in terms of like in magnitude, so I guess like the model you use for the lab doesn't really work in like commercial size. So do you use that model and like keep changing as you scale it up, or how is that process like?
So what you do is you use your lab scale model, gives you a conservative approach or a conservative starting point for your commercial application. So you want starting from scratch on a commercial machine. It'll give you a good approximation, and then you sort of have to fine tune your larger equipment to make sure that you're as efficient as you can be and your product comes out the way you want it to. But the most important thing is to have that starting point. Otherwise, you have to redo the entire research that you've done on a larger scale, which is, extremely, extremely expensive. So that's the motivation.
Okay, thank you.
All right, so we're at the end of the event. So we are going to be doing a Kahoot based on the things our speakers have presented. So if you wish to participate and win a gift card, I do highly recommend that you try the Kahoot. Let me just start it up. Okay. So I'm gonna share my screen. Oh, that's odd. I think that's everybody that wants to join. Is there anybody else that still needs a minute? Okay, so I will be starting the Kahoot now. Nice.
Mm.
Okay, last question. Okay, congratulations, Sandy. You will be contacted shortly afterwards for a gift card. Okay, so the last thing that we want to finish off with is our closing raffle and Easter egg raffle. So you can scan the QR code right there and give us feedback, and you will be entered in a feedback raffle. And if you get the number of Easter eggs that were correct, you are also going to be eligible for a second raffle. for those that participated in the Kahoot, there is a quick correction with the gelatin complex one. It's gelatin complex, not chelation complex. I just did that as like something to trick you guys for the Kahoot, but I might have messed it up when I was finishing up the Kahoot. Okay,
Best thing to leave it alone rather than go back over the whole thing.
I know, but just saying it, just to acknowledge it. Thank you, Folake. So this is the end of the Cafe Research panel. I hope that all of you had a good time. I want to thank our speakers for coming. And you guys can have a great evening. We will announce the raffle winners later on and you will be contacted. So please fill out this form and we will contact you telling you exactly if you've won or not. All right, so you all can be on your way or stay and chill if need be.
Thank you for doing this. It was a wonderful evening. Thank you.
Yeah, thank you very much.
Thank you for having me.
Thank you for having
Oh my gosh. And my children, obviously.
Thank you. Have a nice night.
Yeah, thank you so much.
Have a
Thank
good
you.
evening, everyone.
You too. Thank you. Hello.
Hey, yeah, that would, oh shit, I forgot.